Hello students, welcome to lecture number 2 of module number 2. In the last video lecture, we discussed about the formation of a p-n junction and the immediate after effects of the formation of a p-n junction. That means, what will happen to the junction immediately after you form the p-n junctions. That we discussed in the last class. In the today's lecture, we will discuss what will happen if you will bias a p-n junction. That means, what will happen if you will apply an external potential to a p-n junction, and that's called biasing a junction. But before going into the detail of biasing a p-n junction, let us have a recap what we studied in the last class. In the last class, we studied how to form a p-n junction with a condition of continuity, no irregularity at the surface of the junction. How you can form a p-n junction without any deformity, without any discontinuity at the junction of p side and n side. Now, after forming the p-n junction, we discussed or we studied that a depletion layer comes into place with a potential difference developed across the p-n junction. And a depletion layer means it is a region which is depleted of the free charge carriers. It is a region where there will be no free charge carriers. Only there will be immobile ions. That region is called as depletion region or space charge region. As a result of depletion of these free charge carriers, the depletion region will develop a potential, and that potential is called barrier potential or barrier height. The potential will be positive in the n side of the junction, and the potential will be low or negative in the p side of the junction. And as a result of this potential, an electric field will be developed pointing from n side to the p side. And the height or the value of that potential V0 is called height of the potential as shown in this figure. The physical distance of the depletion region across the junction is called barrier width. Now, at equilibrium, the diffusion current will be exactly equal to the drift current. At equilibrium means at a time after which no further action is going to take place, no further mechanism is going to take place. That's called equilibrium. At equilibrium, the diffusion current is exactly equal to the drift current. The diffusion current results due to the diffusion of majority charge carriers across the junction, and the drift current results due to the drift of charge carriers, minority charge carriers across the junction. And at equilibrium, the diffusion current will be exactly equal to the drift current, and they are opposite to each other, so that the total current will be equal to 0. If the diffusion current is from left to right, then the drift current will be from right to left, so that the total current will be equal to 0. The most important point is that this potential barrier developed will restrict further movement of majority charge carriers across the junction. That means, since this potential developed is having positive potential across this side, and holes, positive charge holes are the majority charge carrier on the p side, this potential will not allow further movement or further diffusion of majority charge carriers from P side towards N side. At the same time, similarly, since this potential is negative or low potential and the majority charge carriers in this side are electron, this potential will not allow further movement of electrons from N side to the P side, that will restrict that. However, this potential barrier, this potential height will allow or will support the movement of minority charge carriers. That means, since this is positive potential and electrons which are negatively charged particles in this region P side, hence this potential will attract them to pass through from P side to N side. Similarly, since this potential is negative and holes are the minority charge carriers in the N side, this potential will attract or allow the movement of minority charge carriers from N side to P side. Therefore, this barrier potential supports the movement of minority charge carriers across the junction. Please keep this in mind that the potential barrier restricts the further movement of majority charge carrier across the junction, whereas this barrier potential supports the movement of minority charge carriers across the junction. These facts are going to be used for further discussion on biasing of a semiconductor. Now, a semiconductor diode is basically a PN junction with metallic contacts provided at two ends for the application of an external voltage. Now, what is a junction diode? Junction diode is basically a junction, PN junction, in which two metallic contacts are provided at both ends, this end and this end, so that you can supply potential if you want, when you want. Now, biasing is a process in which we provide some external potential to this PN junction diode in order to alter the depletion region according to or as required by the device application, by our device application. As we require for our device application, we used to alter the depletion region or width of the depletion region or height of the depletion region by supplying appropriate potential, and that supply of appropriate potential is called biasing. Now, depending upon the polarity, since there are two polarities only for potential, one is positive and one is negative, there are two kinds of biasing, and one is called forward biasing and one is called reverse biasing. And this is a symbol for a PN junction diode, where this triangle is denoting P side of the diode and this bar is denoting N side of the diode. Basically, this arrow is defining the direction of conventional current when you are biasing the PN junction in forward direction. When you are biasing the PN junction in forward direction, the direction in which the conventional current will flow, conventional current means the direction in which holes will flow, or the direction opposite to the flow of electron, that direction is called conventional current direction. This arrow sign denotes the conventional direction of current when you are forward biasing the PN junction diode. Now, let us discuss what is forward bias. Let us consider a PN junction diode in this way. This is a PN junction diode immediately after form, where a barrier potential of height V0 has been generated, and this barrier potential is 0.3 volt for germanium and 0.7 volt for silicon. Now forward biasing means when the positive terminal of the battery, this battery is connected to the positive P side and the negative terminal of the battery is connected to the N side, we say that the p-n junction diode is forward biased. Please remember, when the positive terminal of the battery is connected to the P side and negative terminal of the battery is connected to the N side, we say that the p-n junction diode is forward biased. Now hold for a moment. Think what will happen if we will bias the p-n junction diode in such a way. If we will bias the p-n junction diode in this way, then since this is a positive terminal, this will push these holes further towards the junction. Since holes are also positively charged and this terminal of the battery is positive terminal, this positive potential will push these holes towards the junction. Similarly, the negative terminal of the battery will push these electrons towards the junction. Since electrons are negatively charged, this negative terminal of the battery will push the electrons towards the junction. Then what will happen? Some electrons and holes will come towards the junction and the width of the depletion layer will decrease. If the width of the depletion layer is decreasing, then the height of the barrier potential will also decrease. That means after biasing the p-n junction diode with an external potential of V, where the barrier potential of the p-n junction, original barrier potential of the p-n junction diode was V0, the effective potential of this forward biased p-n junction will be V minus V0 and the depletion region will decrease and the electric field from N to P will also decrease. And the effective potential of this depletion region will now be V minus V0. Now as a result of this movement of holes from this side to this side and electrons from this side to this side, a diffusion current will come into picture. That means some electrons from this side, since the depletion region has now been decreased, some electrons from this side and some holes from this side will get enough energy to cross over the junction since the depletion region has been decreased. Now once electrons from this side has been crossed over to this side, the electrons becomes the minority charge carrier here. Similarly, the holes after crossing to this side, holes will become the minority charge carrier here. Now since these are minority charge carrier and the concentration of minority charge carrier here is less than the majority charge carrier, these minority charge carrier means holes will diffuse from here to towards the end of the junction. Since because of the carrier concentration difference, the majority charge carrier concentration charge carriers are electrons here and minority charge carriers are holes. Now once these majority charge carriers from P side cross over the junction, they becomes the minority charge carriers in N side, and due to the concentration difference, they will diffuse from the side of the junction or near the junction towards the end of this semiconductor diode. And this diffusion of holes from here to here will consist of a current called diffusion current due to holes. And this process of injecting minority carriers from this side to this side is called minority carrier injection. That means in forward bias we inject some carrier which are majority charge carriers in this side, but after crossing over to this side they are becoming the minority charge carriers. and due to the concentration difference they will diffuse from near the junction towards the end of the junction diode, and that diffusion will be consisting of a current called diffusion current due to holes. Similarly, the electrons after crossing from this side to this side, they will become minority charge carriers here, and they will diffuse from the side of the junction or near the junction towards the end of the p-n junction diode, and that diffusion will be resulting a current called diffusion current due to the electrons. Now, the total current in the diode or external circuit will flow from this direction to this direction in which holes are moving. That is called conventional current direction, and the total current will be equal to the current due to diffusion current due to holes plus the diffusion current due to electrons. Now, if you further increase the biasing potential, then what will happen? Slowly the depletion region will decrease. The width of the depletion region and the height of the depletion region will decrease, and at a time, the entire depletion region will vanish. The potential of the depletion is suppose V naught, then at a applied potential V equal to V naught, this entire depletion region will vanish, and the diode will conduct after that like a conductor. That means the conductivity of diode will be increasing, and after that the current will be proportional to voltage. If you are further increasing the voltage, there will be further increase of current accordingly, and this is called forward bias. Now, let us have a recap what we discussed now. Now, when you forward bias a p-n junction diode by giving a positive potential to the p side of the material and negative potential to the n side of the material, the free electrons are repelled by negative terminal and the holes are repelled by the positive terminal. So, some holes and some free electrons enter into the depletion region. As a result, the potential barrier and width of the depletion region decreases. The potential barrier height and width of the potential region decreases. The effective barrier height under forward bias is V naught minus V, where V naught is the barrier potential just after the formation of p-n junction and V is the supplied potential. Therefore, a large number of majority carriers will pass from one side of the junction or will cross over from the one side of the junction to the other side of the junction through the depletion region. Once they cross over the junction, the majority charge carriers becomes the minority charge carriers in the other side. For example, holes in the n region and electrons in the p region. Holes in the n region and electrons in the p region become minority carriers, and this process in forward bias is called minority carrier injection. We are just injecting some carriers to the other side of the junction, which are becoming the minority carriers in that side of the junction. Now, at the junction boundary on each side, the minority carrier concentration increases significantly. The minority carrier concentration increases compared to the locations from the far of the junction. From this side of the junction, nearby the junction, from this side of the diode, nearby the junction, the minority carrier concentration increases. And due to this concentration gradient, there is a difference in concentration. The injected electrons on p side, diffuse from the junction edge to the other side of the p side material. Similarly, the injected holes in the n side diffuse from nearby the junction to the other edge of the n side. This motion of charge carriers on either side give rise to current. The total diode forward current is the sum of hole diffusion current and conventional current due to electron diffusion. The total current will be equal to the addition of Hall currents and Hall diffusion current and electron diffusion current. Now, the magnitude of this current is usually in milliampere. The magnitude of this diffusion current when you are completely removing the depletion region by supplying some potential will be in the milliampere range. Now, let us discuss, let us see what will happen if you will reverse bias a PN junction diode. Now, when the negative terminal of the battery is connected to the P side and positive terminal of the battery is connected to the N side, then the PN junction diode is said to be reverse biased. In this picture, in this figure, the negative terminal of the battery, this terminal of the this side of the battery will be connected to the P side, and the positive terminal of the battery is connected to the N side. Now, as a result of this positive terminal will attract these electrons of the N side, which are the majority charge carriers of the N side. At the same time, this negative terminal will attract the holes, which are the majority charge carriers of the P side. As a result of this attraction, this barrier width has increased, and hence the barrier potential, effective barrier potential also increases. The effective barrier potential in this case will be equal to V plus V naught, and hence the electric field from N side to P side, pointing from N side to P side, will also increases. Now, if the barrier width increasing and hence the barrier potential increasing, they will not allow the movement of majority charge carriers from P side to N side or from N side to P side. That means this increases in effective barrier potential in the case of a reverse bias will restrict the movement of holes coming from P side to N side and the movement of electrons coming from N side to P side. So, the current due to diffusion of majority charge carriers will decrease in comparison to forward bias. Since the majority charge carriers are not able to diffuse due to the increased effective barrier potential, the diffusion current will decrease in comparison to the forward bias. However, the minority charge carriers in the P side, which are electrons, and the minority charge carriers in the N side, which are holes, those are supported by this barrier potential. The holes in the N side, somehow if they are coming nearby to the junction, they will be drifted or swept out by this negative potential, effective negative potential of the barrier. Similarly, the minority charge carriers, which are electrons in the P side, somehow if they are coming nearby to the junction, they will be swept out by this barrier potential, effective barrier potential to this side. And due to this drift of minority charge carriers from P side to N side and from N side to P side, a very small amount of current will be there in the external circuit. This current is due to the drift of minority charge carriers from one side of the junction to the other side of the junction. Now, this current due to the drift of minority charge carrier is very small in amount, which will be in the range of microampere. This is because the minority charge carriers are very small in amount in each side of the PN junction. In each side of the PN junction, the minority charge number of or concentration of minority charge carriers is very small, and hence the current due to the drift of minority charge carriers under the condition of reverse biasing the PN junction will also be very small. Now, this current is called reverse saturation current. This is because the minority charge carrier in any kind of in P type or in N type semiconductor material is temperature dependent. that they are getting generated intrinsically due to thermal agitation. Therefore, as long as the temperature is constant, the number of magnetic charge carrier is constant. So, if the number of magnetic charge carrier is constant, the current due to magnetic charge carrier will also saturate. That means, if you will increase the potential, barrier potential, reverse bias barrier potential slowly, the magnetic charge carrier will increase, but after some time it will saturate. After some time, if you will further increase the barrier potential or supplying potential, biasing potential, the magnetic charge carriers or the reverse current will not increase, that will saturate to a certain value. That is why it is called reverse saturation current. But a point will come at which the current due to magnetic charge carriers, the reverse saturation current will shoot, that will increase suddenly to a very large value. That potential is called breakdown potential, and it is the potential at which avalanche breakdown does take place in a semiconductor diode. We will discuss sometime about the detailed procedure of avalanche breakdown, but for time being, you just remember that in avalanche breakdown, lot of number of magnetic charge carriers will be generated on the both side of the p-n junction diode, and as a result of that, the saturation current or reverse saturation current will increase suddenly at a certain potential, that is called breakdown potential. Now let us have a recap of what we discussed now. Now when you are reverse biasing a p-n junction diode, the direction of applied voltage is same as the direction of potential barrier. The potential barrier has a direction negative this side and positive this side, and in the same direction we are applying a potential negative this side and positive that side. As a result, the holes in the p region are attracted by the negative terminal, and the electrons in the n region are attracted by the positive terminal of the battery. Therefore, the barrier height and the barrier width, depletion region width will increase. The barrier height will also increase, and the depletion region will also widens due to the change in electric field. Now the effective barrier height under reverse bias will be V0 plus V, where V0 is the original barrier potential just after the formation of p-n junction, and V is the applied potential. Therefore, the flow of electrons from n to p side, and the holes from p to n side will be restricted, and therefore the diffusion current decreases enormously compared to the diode under forward bias. The diffusion current due to electrons and holes will decrease enormously in comparison to the forward bias case. But the potential barrier helps the movement of magnetic carriers. As soon as the magnetic carriers comes closer to the junction, due to their random motion, they will be swept away by the potential barrier to the majority zone. That means, if the electrons are magnetic carriers here and somehow they are coming nearby to the junction, they will be attracted by the potential barrier and they will come to this side where they are majority charge carriers. Similarly, if the holes are magnetic charge carriers here and somehow they are coming nearby to the junction, they will be swept out or they will be supported by this potential difference, and they will come to this part of the diode or this side of the diode where they are majority charge carriers. This drift of magnetic charge carriers gives rise to a current called reverse saturation current, and it is in the range of microampere due to small number of magnetic carriers. Since magnetic carriers are small in numbers, this current will be small in number. It will be in the microampere range. Since the rate of generation of magnetic carriers is constant at a given temperature, as the magnetic carriers are nothing but the intrinsically generated carriers, Therefore, the resulting current is constant irrespective of the applied voltage. However, you are changing the voltage, the reverse current is not going to increase. The reverse current due to magnetic charge carriers, drift of magnetic charge carriers is not going to increase. For this reason, this current is called reverse saturation current. However, the current under reverse bias is essentially voltage independent up to a critical reverse bias voltage. Up to critical reverse bias voltage is only the reverse saturation current is voltage independent, and that voltage is called breakdown voltage. When the applied voltage will be equal to breakdown voltage, the diode reverse current increases sharply. Suddenly it will increase, and the slight change in voltage after this will cause a large change in the reverse current, reverse saturation current. If the reverse current is not limited by an external circuit below the rated value, if the rated value of reverse saturation current is VBR, then that reverse bias current voltage, this reverse bias voltage or this reverse bias current should be below that rated value. If it is not below that rated value, the PN junction will get destroyed. If you are increasing the reverse bias potential beyond VBR, so that the reverse saturation current will sharply increasing to a very large value, the PN junction diode will get destroyed due to overheating. Some high temperature, lot of heats will be generated due to high current, and the diode will get destroyed. The reverse biased PN junction diode has an effective capacitance. Now, the P region and N region, this P region and N region will act as the plates of the capacitor, and the depletion region will act as the dielectric medium of the capacitor. That means, under reverse bias, a PN junction diode behaves as a capacitor whose effective capacitance is called transition or depletion capacitance, and the P region and N region of the diode behaves as a plates of the capacitor, and this depletion region behaves as a dielectric medium of the capacitor. Now let us summarize whatever we discussed on the biasing of a PN junction diode. That summary will be in the form of a plot called VI characteristics or diode VI characteristics. The VI characteristics is basically a plot between the voltage and current across the diode. That means this plot, VI characteristics of a diode, gives us the information about how the current across the diode will change with respect to a change in the voltage. This VI characteristics is its internal characteristics. When a diode will be manufactured, its VI characteristics will be fixed. You just need to do an experiment to plot that VI characteristics, and you have to design your devices for your particular applications as per the VI characteristics. That means, for designing any device for your particular purpose or applications using a diode, you definitely require the VI characteristics. Now, in order to plot the VI characteristics, this is the circuit diagram in case of forward bias. This is a diode. In this diode, this is the positive terminal, this is the negative terminal, this is the positive side, this is the negative side. This diode is connected with a battery along with a resistance, and on the resistance basically it's called a rheostat. It's not a resistance, it's a rheostat. It's a variable resistance, so that if you change the resistance, if you change this key, this arrow is a key. If you change this key on this rheostat, the voltage across this diode will change. The voltage across this diode will change. And obviously, since this is positive terminal of the battery and this is negative terminal of the battery, and since this positive terminal is connected to the P side and the negative terminal, obviously I'll plot that the negative terminal is connected to N side through a milliammeter, hence this diode is forward biased. This diode is forward biased. Only thing this rheostat will do is to change the voltage across the diode, because we are trying to plot the voltage versus current plot of this particular diode, and that's called VI characteristics. Now to measure the voltage across this diode, of course this is a DC voltage. To measure the voltage across this diode, we need to put a voltmeter also here. This is a voltmeter, DC voltmeter, which will measure the voltage across the diode, and this is a ammeter which will measure the current across the diode. Now let us plot the voltage versus current. The current is in the the voltage is in the x-axis, that is called forward voltage, and the current is in the y-axis. Now to make this plot, or to arrive at this plot, we just have to change the voltage across this diode by changing the position of this key on this rheostat, and accordingly we have to measure the current in the circuit, and we have to plot this voltage versus current. Now when you will start increasing the voltage across this diode, the current across the diode will start increasing slowly till a point which is decided by the barrier potential. Till the moment you are cancelling the over barrier potential and you are decreasing the barrier width to 0, till that point that current will increase slowly. After that, if you increase the voltage, that current will increase with directly proportional relation with the voltage. This region is called linear region, which is beyond that point, beyond the point at which you are just balancing the voltage barrier potential across the diode with the applied voltage. Because if it is a forward bias, then the effective potential will be V minus V naught. If it is a forward bias, effective potential will be V minus V naught. Now if you will start increasing V, a point will come when V minus V naught will be equal to 0 and there will be no depletion region. Till that point, the current will increase slowly. Without following a linearity. After this point, the current will increase linearly. That means the relation between voltage and current will be linear. From which the relation between voltage and current will be linear, that is called knee voltage. Of the diode, and which is obviously will be equal to the barrier potential. Once you balance that barrier potential, then after that there will be no depletion layer, and there will be no obstruction for movement of charge carriers, and the semiconductor diode will simply behave as a conductor. This is the case of a forward bias. Now let us see what will happen in case of reverse bias, and we discussed this is the circuit diagram of a reverse bias, and here in this circuit diagram the only difference is that the diode has been now just reversed. Now the N side of the diode is connected with the positive terminal of the battery, and the P side of the diode is connected to the negative terminal of the battery, and that's how this configuration of this circuit is reversed bias. This diode is now reversed bias. Now in this reverse bias condition, what will happen if you will increase the voltage across the diode? Now in case, as we discussed, in case of a reverse bias, if you will increase the voltage across the diode, then the effective barrier potential will be equal to V plus V naught. That means the barrier height will also increase and the barrier width will also increase. As a result of that, there will be no movement of majority charge carrier from one side of the diode to another side of the diode, for which there will be no forward bias current, there will be no diffusion current. Only there will be some drift current which is arising due to movement of minority charge carriers from one side to another side. And the current due to this drift of minority charge carriers from one side to another side is limited because the number of minority charge carriers are temperature dependent. They are intrinsically generated, as we discussed in during our study in material. And as long as the temperature is constant, the number of minority charge carrier is fixed and they are not going to increase. Now that reverse bias current will be constant as long however you increase the potential, and that current is called reverse saturation current. So if you increase the reverse voltage VR along across this diode, and if you are increasing this potential, then the current, reverse current, will go on almost as a straight line on this plot, almost as a straight line. The value is very small, that comes in microampere range. This current is in milliampere range, but this current will be in microampere, as few microampere. But at a certain value of this reverse bias potential, as we discussed, there will be a breakdown, that is called average breakdown, and at that point the current will increase suddenly. Once the reverse bias potential reaches that breakdown voltage VB, that breakdown voltage, the current suddenly increases to a large value. If you are increasing the biasing voltage further, then the current will increase to a very large value. And if current is increasing to a very large value, due to the resistance of the diode will be heated. The diode will be heated. The temperature of the diode will increase, and afterwards or suddenly it will burn. So this, whenever you will purchase a diode, they will give you this plot, this IV characteristics. They will inform you about this knee voltage, after which the current voltage relationship in case of forward bias will be linear, and they will be informing about this breakdown voltage, after which there will be a breakdown and your diode will burn. So you should always be careful of the fact that in case of reverse bias, you should not go beyond this value of breakdown voltage. Obviously in diodes this breakdown voltage comes in the range of 100 volt, 70 volt, 80 volt. It's not easy to go to that level, but you should take care of these things. Now in this forward bias, since this is a linear region, that means this is also called as ohmic region. What is ohmic rule? Ohmic rule says that the current and voltage across a resistive element is directly proportional to each other. I mean, the ratio between voltage and current is equal to a constant. That constant we call as resistance. And if the current element or the element is behaving in this way, means voltage divided by current is equal to a constant, then that element is called an ohmic element. So in this linear region, the diode is behaving as an ohmic element, and that's why this region is called as ohmic region, OHMIC, ohmic region. Now if it is a linear region, always we can define a resistance in this region. We cannot define an average resistance in this region. We have to define the resistance at each point separately. At each point the resistance will be different. But for this linear region, the resistance will be constant for the entire region. So we can define that a resistance for this point, and that resistance is called static resistance or DC resistance, and that is given by the formula RDC equal to V divided by I. And this RDC equal to V divided by, of course that is valid for all regions, but those are not static resistance. Their resistance will be changing. till the moment the diode is coming to this knee voltage, till the moment your supply potential is coming to this knee voltage, the resistance of the diode will not be static. The resistance will be changing. But once it will cross this region, this voltage, the resistance of the diode will be static. That's why that is called static resistance or DC resistance. So static resistance will be equal to RDC equal to V divided by I. Now if after biasing this diode on the top of this biasing potential V0, if you will apply a AC current along this diode, then the AC resistance of the diode will be equal to change in voltage divided by change in current, that is called AC resistance. We always operate our diode in this linear region. We always operate our diode in this linear region, and that in that linear region, if you are supplying a AC voltage to the input of the diode on the top of this biasing voltage V0, then that AC resistance of this diode for that particular signal will be equal to delta V divided by delta I. That's called AC resistance or dynamic resistance of the diode. Now let's have a recap whatever we discussed recently. In the above circuit, this VI characteristics, a milliammeter is used in the forward bias circuit since the expected current is large, while a microammeter is used in the reverse bias circuit since expected current is small. Now in forward bias, the current first increases very slowly. In case of forward bias, the current first, if you remember the figure, the current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value called threshold voltage or cut-in voltage. That voltage is called threshold voltage or cut-in voltage. Now cut-in voltage is approximately 0.2 volt for germanium and 0.7 volt for silicon, and these are normally equal to the barrier potential of the diode. For the diode in reverse bias, the current is very small, which is in microampere range and almost remains constant with change in bias, and is called reverse saturation current. For special cases at very high reverse bias breakdown voltage, the current suddenly increases. That's called breakdown of the diode, and at applied voltage equal to breakdown voltage, there will be high current. Suddenly the current will increase. This shows that the PN junction diode allows the flow of current only in one direction when it is in forward bias. When the diode is in forward bias, the resistance of the diode is very low as compared to the reverse bias resistance. In case of a reverse bias, the PN junction diode do not allow the flow of current because the current is coming very less, that is in microampere range. So basically the PN junction diode allows flow of current when it is forward biased, but the PN junction diode do not allow flow of current when it is reverse biased. And this property will be using for a device application that's called rectification of AC voltages in the next few coming classes. And we defined the dynamic resistance as the ratio of small change in voltage delta V to small change in current delta I when the diode is operating in the linear region. So this was all about this class, where we discussed the forward bias, how to do forward biasing, and what are the effects of diode when you are forward biasing the diode, and how to do reverse biasing, and what are the effects in the diode when you are reverse biasing the diode, and what is the VA characteristics of a diode, and different characteristics and different important points of the VA characteristics of the diode we discussed. In coming classes we will discuss how to use this VA characteristics information of a diode to achieve some device applications for our purpose. Thank you.